ऐसे फॉरेन के ऊपर आई तो 2026 में फ्री ऑप्शन में पैर
జాయిన్ అవునా సెటప్ లోనే కాలేదు అది యూట్యూబ్ లో జాయిన్ అయ్యాను యూట్యూబ్ ఏం వెళ్ళరా
నేనేం చేసినాను రా మధ్యలో నా మీద పడతారే.
వాకింగ్ ఒకటే అవ్వదు, నేను అదే.
వీడియో ఆన్ చేద్దానా ఒకసారి. రా.
ఏమన్నా
Hello. Good morning. Good morning, everyone. Hello, it's audible. Good morning, everyone. It's audible.
Yeah, ma'am. Good morning, ma'am.
Yeah.
I'm the CSC faculty, Malati, ma'am.
Okay. Good
Some
morning.
people are now joining, ma'am.
Okay. Okay.
Has to wait for 2 or 3 minutes, ma'am. They are joining. ma'am.
Okay. Okay. Fine. Let them.
Okay, ma'am. Thank you.
Kindly inform me when I'm supposed to start. Malti ma'am. Hello, Malti ma'am.
అక్క పిలుస్తానండి నేను పోయేస్తాను వస్తాను ఇప్పుడే చేయాలి మీరు చూపిస్తా
Hello. Hello. Please mute everyone.
హలో
Malti ma'am. Can I start? Can we start, ma'am? Ma'am, can we start?
அது நான் என்ன பண்றோம்
Everyone, please mute.
Absent, sir.
Ma'am, good morning, ma'am.
Malti. Good morning, Malti ma'am.
Ma'am,
It's
Dhanashree,
audible. It's audible. It's
ma'am.
audible. It's audible.
Ma'am, kindly start the session, ma'am.
Ma'am, it's audible.
Yeah, ma'am, audible, ma'am.
Yeah. Good morning, Malti ma'am.
Good morning, ma'am.
Can we start now?
Okay, start. Yeah, ma'am. Start now. Start the session, ma'am.
Okay, fine.
Okay, thank you, ma'am.
Okay, fine.
Mm.
1 second. 1 second. Share entire screen. PPT is visible. PPT
Yeah,
is
ma'am,
visible.
visible, ma'am. Yeah, ma'am, visible, ma'am.
Fine, fine. Okay, so dear students, last class, what all topics we covered? You need to communicate with me. Last class, what all topics we covered?
Students, kindly answer the question. Yeah, ma'am, visible.
Huh? What all topics we covered last class? Sneha, answer. Sneha? Yes, you need to answer me now. Okay, what is the slide, present slide on the screen? Sneha? Chandana? What is the present slide topic on the screen? Are you there or just you connected online and you left the online room? I want to know. Latish? Chandana? Dinesh? Netaji?
Quantum computing, ma'am.
Okay. See, you people are connected and you are not there in the online. Huh? Okay, fine. Okay, quantum computing only. Which all topics we covered?
Yes, yes.
Huh? Which all topics we covered? One student, unmute and tell. Any one student unmute and tell me which all topics we covered last class. Okay, on the present slide, what is the title?
Quantum computing, ma'am.
Okay, quantum computing only. Your subject name itself, quantum computing. Under that, what we are studying?
What is required to build a quantum computer? Conceptual overview.
Okay, good. So last class, one topic in module 3. Please mute everyone. Okay. Last class, one topic under module 3 we started, that is building the quantum computer. So if you want to build the quantum computer, so what and all conceptual requirements are there. So just we went through that when we try to build the quantum computer, it is very complex. We require some deep expertise in physics, engineering, computer science, all this. And then basic thing, what is the basic platform for quantum computer? Can anyone tell? What is the basic platform for quantum computer? You know, everyone knows. My cursor is moving around where? Huh? Hello. The basic platform for quantum computing is? Dear students. Hello.
Qubits, ma'am.
Qubits. Okay. So we have in this qubits also we have different types of qubits. So you can use superconducting qubits. that leads to different supercomputing quantum computers. You can use trap ions. That will leads to the different, that is the technology of quantum
Qubits.
computer. Yes. Qubits is the basic platform for your quantum computing, but we have types of qubits. One is superconducting qubits is there. So here we are using this superconducting qubits for your manufacturing your. This is the basic concept used in superconducting quantum computing, and another supercomputers are there where you can use trapped ions, and in other supercomputers you can use photonics. That is your photons, your basically your the ray of lights that will be used. Okay, that is the basic platform for your quantum computer. And we have spin qubits. Here we will be using electrons, whatever moving around your nuclear neutrons, electrons will be moving around in the atoms, no, that concept will be used here. And finally you can use topological qubits also. So we have different types of qubits that can form the basic fundamental unit to manufacture your quantum computer. Okay, so the basic platform for quantum computer is qubits, but qubits will be varying. Different types of qubits are there. These are the different types of qubits. So by using these different types of qubits, we can manufacture different types of, suppose if I use superconducting qubits, then it may be called as this particular quantum computer technology is based on superconducting qubits. Suppose if I'm using spin qubits, then I should say that this quantum computer is using the technology spin qubits. That is the platform behind that. Electrons will be used. So if I'm using photonic qubits, then I have to tell that this particular quantum computer, it is designed using the concept of the ray of the light, photons. That concept is used behind the technology of the quantum computer. So this you should understand. So just you should not say that yes, the basic platform for quantum computing is qubits. There are different types of qubits used in different quantum computers. So these are the different types of qubits used in different quantum computers. Now coming here, how to control these qubits? Yes, by controlling these qubits only, you can do all your whatever the operation you want to do, whatever the calculation you want to do, everything you can do. That we need to go through. For that, you can use your microwave electronics, okay, to manipulate that, to measure the output, all that. Laser system also you can use. Okay, and then you can control the software, the entire thing software you can control in your quantum computer by using this pulse shaping, timing, error correction softwares. Then we are using this cryogenic amplifiers. What is this cryogenic concept? What is this cryogenic concept in quantum computers? Can anyone tell? Now you know what is qubits, and you know how to control the qubits. By controlling only, you can do all the manipulation, all the calculation. You can get the whatever the output you want in quantum computers. What is this cryogenics? What is the concept behind this? Can anyone tell? Hello? What is this cryogenics? Please switch off your video and audio. Somebody, who is this Sunita? Put off your video also.
Faculty, ma'am. Oh, wait, ma'am, I will.
Okay, no problem. Sorry. Now tell me, what is the concept behind this cryogenics? Anyone? They are telling. Yeah. Yes. Can you? Because this I already completed last class. Now you should be ready with this. You should know all this concept. Just I'm doing overview only to understand how much you understood. What is this? At least you should know what it is. Cryogenics. Can anyone? Yes. See, when you're trying to manufacture your quantum computers, they require extremely low temperature. Why? Can anyone tell? Yes. Why? They should be at extremely low temperature. Please note down this question, everyone. When you're manufacturing, when you're working with your quantum computers, these computers should be placed at the extremely low temperature. Why? One question. Next class you should answer this. Okay. Okay. So coming here, next is that the one main thing is there when you try to build the quantum computer, error correction. And you know the characteristics of your quantum bits. This quantum bits, whenever it is trying to interact with the environment, due to this cosmic rays, electromagnetic rays, and all, it will try to change its behavior. It will collapse. Okay, so automatically, whatever the output it is showing, the output will keep varying. So that is the main drawback in your quantum computing. So because of that, it's the behavior of the qubits. So we have so many error correction strategies to correct this, so that we get the correct output. So this is one disadvantage in your quantum computers. Now coming to next is quantum architecture and scalability. And you know very well, in your classical computers you have studied so many architecture. Here also we are following the different quantum architecture, and we try to interconnect with fiber optics. We use photon rays or microwave lines, like this we will use, and we try to connect the all your system in the quantum computers. Then control system and software, we are using this quantum programming language, Qiskit, okay, all this. And we have quantum compilers. Similarly, other compilers, whatever you're trying to use in classical computers, similarly, we are using here also. And we have control software, control hardware for real-time execution and feedback. These are the things. And then material science and fabrication, they'll choose high purity material, like low defect silicon, like that. And non-fabrication facilities like clean rooms and all is required, and that should be maintained at low temperature, your quantum computers and all. This and all, it's a basic needs for building your conceptual concept behind your quantum computers. And when you are working with the quantum computer, you require all the expertise. Who and all physics people is required, electrical RF engineers is required. What is this RF? What is RF? Can anyone know this? What is RF engineers? Dear students?
Radio frequency.
Good. Radio frequency engineers and cryogenic engineers, software developers, material scientists, and all these theorists, some theoretical knowledge you have on this quantum computers, information, and also who is good at quantum algorithms. Okay. See, when you're working with quantum algorithms, the fastness is very much important, because we are working on super computing, right? So we are going to follow so many different algorithms that will help you to do the calculation much faster. And that is the concept behind your quantum computer. And when you try to develop your create your manufacture your quantum computing, massive funding is required. It requires millions to 100 millions in R&D department. So this is the basic requirement to build your quantum computer. That is one topic we discussed. Next topic we discussed, fragility of the quantum system. Okay, what is this fragility of the quantum system? One disadvantage in your quantum computer is fragility to quantum system. It is prone to error. Two things: fragility to quantum system and prone to error. What is this fragility? What is fragility? Can you tell? What is this? Your quantum system will change rapidly when there are causes will be there. What are the causes for this fragility? One is decoherence, another one is noise, another one is gate error, another one is crosstalk, another one is measurement error. So you know very well, because of behavior of your qubits, whenever it is interacting with the environment, because in our environment we are surrounded by noise, electromagnetic rays, cosmic rays and all. Once it starts interacting with the environment, there will be sudden change in the behavior of the qubits. So it will start collapsing, and then whatever the output we are getting, randomly it keeps changing. Okay, so we can't do anything. That is the behavior of the qubits. So that one reason is that is decoherence. Okay, till your qubits is working for you, giving you the correct output. You are using it in proper way and you are getting the correct output. That time is there. No, that is known as coherence. Whatever the useful activity you are getting correctly, everything is going on. Your qubit is acting very nicely with you. Okay, that time period is known as coherence time. Okay, always we expect long coherence time. We need long coherence time, but that is not at all possible in case of qubits, because behavior of the qubits itself, whenever it is interacting with the environment, it will change and it will collapse, and then your output will change. That is known as decoherence. Once the qubit behavior changes when it is interacting with the noise and all in the environment, that is known as decoherence. This is also one reason for fragility of the quantum system. And noise, in the environment, we'll have different types of noises. Due to that also, your quantum bit behavior will change. And we have gate errors. This is your generally, you have the great quantum gates that is supporting for manufacturing your system. That also will have error, and crosstalk and all we discussed last class. Okay, if you are doing some changes, you go with the dense quantum computing. Okay, hello, are you able to hear me, students? Hello.
Yes, ma'am. Yes, ma'am.
Okay, 1 second. Fine. And finally, the measurement error, you people know, you should know this. That is what, whenever when the noise affects, whenever due to the noise, your behavior of the qubits will change, then the output also will change. Okay, then we have to properly handle the input. You should do it such that we have to wait, and then you have to measure the output. The how can you overcome this measurement error? You have to give proper shielding to your quantum computer. It should not interact with the environment. Then you can overcome this measurement error. If you do properly shield your quantum computer so that you should not interact with the environment, okay, then your measurement error can reduced. Okay, that is one thing. So coming to next one, these are we discussed all these points under the fragility of the quantum system. Then coming to this one, if you want due to all this reason, due to this error, I want my system quantum computer should work stable. And like now we have because nowadays what is happening, whatever the present quantum computer what we are working on, it is a small the number of qubits is small in size, but the research is going on. Further they want to increase the number of bits of the qubits, they want to increase. Okay, if they increase this whatever the fragility to quantum system, error correction and all will become more and more. That is why the research is going on further. The trial error is going on. They want some stability, they want some conditional functional quantum system. Now whatever the quantum system is existing, it is of only a few qubits. Okay, the number of qubits may be some less, but we want to generate huge supercomputing quantum computer. Then the number of qubits we should naturally increase. As we are increasing the qubits, your fragility to quantum system also will increases, and error also will increases. That is why the research is going on. So if you want the functional quantum system to be work properly, what are the needs? First of all, your quantum system should be isolated. Why? You know very well, because of the behavior of the qubits, once it is interacting with the environment, the behavior changes. It will come from coherent state to decoherent state, and whatever the output you are measuring also will change. So you have to isolate. They are telling a quantum system must be shielded from its environment to preserve the coherence. So this is one condition, very much important, to make your quantum computer work properly. Then you have to do proper error and management. Then you have to focus on scalability. Scalability, if you want to increase the qubits, if you want much computer, then you have to increase the qubits. You have to increase, then once you increase the qubits, definitely it
Ma'am, not
leads
audible, ma'am.
to more error. Okay, because you know stability. What is the stability they want? They want consistent operation. For the noise, not audible. Once again, wait.
Not audible, ma'am.
Once again, once again.
Not audible, ma'am.
Once again, once again. Okay.
Students, wait for some time. Again, you are asking not audible.
Once again. Now it's audible. It's audible now.
Yes, ma'am.
Yes, ma'am. Yes,
Fine,
ma'am.
fine,
Yes,
fine, fine, fine. One second, wait now. Can you see my screen? PPT is
Yes, ma'am.
Fine. Okay, so these are the condition. If you want to make your quantum computer functional properly, we have to follow all this concept. What and all? You have to isolate the quantum computers. You have to do proper error management. Any error is occurring, we have to manage that properly. For that, we are using one concept known as no cloning theorem. What is this no cloning theorem? It will avoid the duplication of the quantum states. So by avoiding the duplication of the quantum states, we can reduce the error correction strategies. Okay, so what they are telling, one way of reducing the error correction strategies in the quantum computer is that you please follow the no cloning theorem. This will help you to not to duplicate the quantum states. If you do duplication of the quantum states, it leads to more error. Okay, so you can use this no cloning theorem and you can avoid the duplication. Okay. And then they want a fault tolerant system. Fault tolerant system means they want long coherence time. That means system should be always stable, as our classical computer. Always, whenever you are giving input properly, when you are running some algorithm, when you are giving this input, you will get the correct output, right? Similarly, your quantum computer also should be always stable. Whatever input I'm giving, your algorithm should process that, you should get the output. But because of the behavior of the qubits, when it is interacting with the environment, if proper shielding is not given, proper isolation is not given, definitely your output is going to change. So but we want to manage proper fault tolerant system by managing the errors and all properly. For managing the errors also, they are following one thing. What is that one? They are using this threshold theorem. Okay, when you're using this threshold theorem, even though error is occurring, definitely because of the behavior of the qubits when it is interacting with the environment, error will occur. What they are trying to do by applying this, by following this threshold theorem, they assure that below certain error rates, whatever the error rates you are getting, below certain error rates, they'll fix on threshold. So then for that thing, whatever the logical error, that programming logical error going to occur, that they want to make it small or they want to suppress it. That is the concept they are trying to manage. All they are following this no cloning and threshold theorem, and they are trying to reduce the errors and all. Okay, so last class till here we discussed. Okay, we discussed a conceptual overview how to build the quantum computer, and we understood all the basic requirement that is needed to manufacture the quantum computer. Then fragility to quantum system. Your quantum system will not behave always same because of the behavior of the qubits that you know. So what are the reason for this? Why your qubits are behaving like this? So then we discussed about decoherence, crosstalk, measure error, all that. Then next is that if you want your quantum computer to work standard properly always, you have to isolate, you have to maintain stability, you have to focus on scalability, and you have to manage the error properly. Okay, any doubts here? Last class? These are the topics we covered last class. Any doubts here? Students? Hello? Any doubts here? It's audible?
No, ma'am.
Concept is clear till now?
Yes, no, ma'am.
Hello? Concept, whatever we thought till now, it's clear. Any doubts you have, you can ask me. If you have,
No doubts, ma'am.
everything is clear?
Yes, ma'am.
Okay, fine. Once again.
Yes, ma'am.
Okay. So next, today we are going to focus on today the next topic in your thing syllabus is that why maintaining entanglement is difficult. They are telling maintaining entanglement is difficult in quantum computing. Your quantum computer is based on two concepts. One is superpositioning, another one is entanglement. But we have to maintain entanglement, but it is very difficult for us to maintain the entanglement. Why it is? They are telling that maintaining entanglement is difficult due to several theoretical barriers. Okay, so and then primarily one is that decoherence. And can anyone tell what is this decoherence? I was just talking about this decoherence. Can you define in one line? What is this decoherence? Anyone? Hello? What is decoherence? What you understood about decoherence? Huh? Come again, please.
It will be having some disturbance.
Yeah, correct. Whenever qubit interacting with the environment, due to noise in the environment, your qubit behavior will start changing. That time output and all will change. That is known as decoherence. A qubit is in decoherence state. Okay, if your qubit is properly going on everything, okay, then your output is also everything is fine. That means your qubit is in what state? If your qubit everything is going on fine, okay, your output also whatever you are measuring everything is fine, then qubit is in what state? Hello? Coherent state. You tell me which is best, to have long coherence or not. In quantum computer, it's a must to have long coherence. Yes or no? See, if your qubit is properly working everything and it is not getting disturbed by any noise, your qubit is working properly, and then you are getting the output also proper output you are getting. No change in the output, correct output you are getting. That state is known as qubit is in coherent state. Now tell me, my quantum computer having long coherence, it is good or not? Please answer this question. Yes or no?
Hello,
Quantum?
madam.
Ah,
Hello.
yeah.
Madam, we have no doubt actually.
Tell
But
me.
in the classical computer is working like coherence always. Why? Because it's a one-step process.
No,
But it's
no.
working.
One second.
Yeah.
Question is not clear. One student mute and you please ask me again.
Madam, the classical computers is working like binary language, just a one-step process, 0 to 1 or 1 to 0 like that. But in the quantum computers is working multiple steps like qubits. In between 0 to 1 in the middle, you're going to conduct in a superposition state. Superposition state, we have to connect it. Example, that entanglement angle, how much area to cover, you're thinking? Entanglements is nothing but one place you're going to sit, you're going to twist the coin. Is the head means another side also we get head. But how much area it will be covered, madam?
It depends. No, it depends. Okay. You see, we have to maintain proper entanglement, but due to this decoherence, environmental noise, and all, it changes. We have to maintain. They are telling.
But classical computers is working like coherence. Coherence means same amplitude, same frequency.
Yeah. Because the behavior of the qubit is like that. Your photons, you're using the basic concept behind that. You're using your light rays. The behavior is like that.
Okay, the quantum systems is basically why? Because so much probability. Why? Because it's rotates like 360 degree. So much optionals it will become.
Yes.
But it's the maximum. It goes decoherence. I think so.
Yes. Why? Once it is interacting with the environment, but noise, due to noise in the environment, it will change.
That's why compare with classical computers, quantum. They have a multiple.
No. See, the basic concept what you're using, transistors, right? Transistor below your gates are made up of transistors. Transistor, we are having only two states. You can make transistor on or off. Okay.
Yes, 0 and 1.
0 1. Only two states are there. So there is no disturbance like in quantum computer. Because here we are using that both the states together, and you're using the concept, so it is doing all this.
Okay. Madam, in the future, they shut out in this kind of disturbance and noise in the future. You want to shut out?
Yes. Another 2 years. Another two years, they are going to get the stability in the quantum computers.
Madam,
now,
in our country, now it's going on only initial stage. It's possible to build on labs. No labs they available, but they study only theoretically.
No. IBM company, they are using quantum computers.
It's going on US and Chinese only. It's going on very peak.
No. Now also in our India, IBM is supporting quantum computers, and you get 10 minutes per month. You can use freely your quantum computer in cloud. It is available.
I think very less bits only they're working. I think so.
Yeah. The size, the qubits is very less in size, but ultimately we are expecting whatever the qubit size varies, the stability should be there in the quantum computation. That is the ultimate goal. Then only you can release that in the market and everyone can work on. Directly they can switch over from classical to quantum.
Madam, my question is, suppose 32 bits to, we will go from 256. The time it's possible to create decoherence, it's become, the bits level will be increased. The decoherence level also the increased, is possible?
Yes, sure. How? Because when you increase the number of qubits, the architecture will become dense. Okay. So when the bits are near, it will become more nearer, right? It will become more nearer. In 256, it will become more nearer compared to 32 bits. So the changes happening in one qubit will affect the other qubit. Since it is very near, the change will happen more faster.
Okay.
So the decoherence will increase.
Madam, another one doubts actually. The cryptocurrency like that, they kept so much password like zeros and ones, so much 256 bits also they given password. But it's quantum technology is 1 second they break the passwords. I think so. The security purpose they have a big threatening in the world. I think so.
Yes,
quantum
yes,
technology.
yes. They are
Suppose,
working.
madam,
Yes,
example, I
quantum.
want to
So
tell.
for this, you should focus on quantum communication. Quantum communication.
Okay.
They are
Okay.
working on that. That we will be discussing in next. Okay, now we are focusing on this basics. Okay.
Madam, suppose we will give one mobile password. Example, we'll give 4 bits. 4 bits is optional only. 16 optional will be there.
Okay.
4
Yes,
into
yes.
4 is 16 optional is there.
Uh,
But one
uh,
fellow, they take my mobile.
uh,
They don't know my password. He's
uh.
trying 16 times. Then
Yeah.
after one, they take optional, then after opening.
Uh,
But quantum computer,
uh,
whatever they thinking, one time is typing, already they guessing,
uh.
immediately they open.
Correct.
Security
Yeah.
purpose, they have a big threatening, I think so. In
Yes,
the
yes. In quantum technology, big thread is there. That is known as quantum thread. That
Okay.
will be focusing on quantum communication.
Okay.
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 Yes. So these are the things which is going on. They are working behind this. Okay.
Okay.
Fine.
Sure, madam. Thank you.
Fine. Now, this is the one thing. Maintaining entanglement is difficult due to decoherence and environmental noise. Okay, and again they are telling very difficult to maintain the entanglement. Why means scalability. As now presently we are working on some 8 bits, 24 bits quantum computer, 32-bit quantum computer. If you increase the number of qubits, definitely the noise will increases or your crosstalk will increases. Then to maintain this entanglement is very, very difficult. Okay. Then hardware requirements. Scaling up requires breakthrough in quantum error correction and hardware design to maintain the coherence across numerous qubits. So if you are trying to scale up, okay, then definitely we have to introduce new quantum error correction strategies. Okay, then only we can get the correct output. Then hardware design also, when you're using your quantum gates, you're trying to design that has to maintain the coherence. Coherence means your qubit should properly behave, and even though it is interacting with the environment, it will try to change its behavior. So you should provide proper shielding to quantum computer so that you have long coherence with the numerous qubits. As you keep changing the qubits also, if your qubits is increasing for the quantum computer, then also it should have long coherence. Okay. But it's very difficult because because of the behavior of the qubits. Then measurement problem. This is another problem in we have to, while maintaining the entanglement is very difficult. As you know that, hello. Okay. So measuring an entanglement particle, please mute. Measuring an entangled particle instantly affects the state of the entangled partner regardless of the distance separating them. Yeah. So as I said, when because of this crosstalk, change in one qubit will affect the other qubit, right? So when you try to measure one output, others also may change. Okay. That is the thing. So that is known as the collapsing nature of the qubits. So we have to overcome this also by you introducing some error correction strategies, or improving your shielding, or you have to isolate properly. All that precautions we are supposed to take. Next is distance limitation. What they are trying to do while when you are maintaining the entanglement, to maintain this entanglement, what they try to do, if it is a long distance, okay, if it is a long distance, then transmitting entangled particles through optical wire or free phase, it is limited by photon loss and signal degradation. So basically the behavior because of this ray of lights, the photon loss and all, if the distance is more, the signal degradation will be there. So what they are trying to do, in center they'll try to use this quantum repeaters. When they try to use, if the distance is more, for in between one end and the another one, and that is transmitting end and the receiving end, then there will be signal degradation or photon loss will be there. If you are using a photon qubits, okay, then at the receiving end we can't receive the information properly. So in between they try to use quantum repeaters. If the distance is more, we can overcome this by developing quantum repeaters, so that we can create the entanglement links over the shorter segment and then connecting them to extend the range. Okay, so these are the concepts. Why the entanglement is difficult means because of decoherence and because of scalability and because of your measurement problem, all this. And we have distance limitation also is there. If the distance is more in center, we have to use quantum repeaters. Otherwise, the signal will degrade by the time it reaches the receiver end. Any doubt here? Students, any doubt here? Hello? Any doubt here?
Students, ask any doubt, unmute and ask the question. If you have any doubt.
No, ma'am.
Okay. One second. Any doubt here?
No, ma'am.
So I will be sharing these PPTs for you and also the notes for these two modules. Okay, I'll be sending that link. You people access that. You can access that. You can go through that. Last class, I gave you some task, right? Hello. Last class, I given you some questions. What are the tasks I gave? Have you are you gone through the task? Answer is ready. What are the questions I gave? What are the questions I gave last class? Anyone? You have to communicate with me. Previous to that also, I gave you some questions on AI tools. When I'm giving introduction, why we should study quantum computing. That also people didn't answer me. Last class also, I gave some questions. At least you have to take the question, you should go through and you have to find the answer for that. Okay, today I asked one question on cryogenics, right? Why we have to maintain these quantum computers at very low temperature? What is the answer for this? Please note down this question, and next class, please, when you are coming, you have to answer me this. What is this cryogenic? Why we need cryogenic engineers when you try to build the quantum computer? Why we should maintain this quantum computer at low temperature compared to your classical computer? What is the need of this? If I don't do this, what will happen? Please, note down this question, and next class, when you are coming, you have to tell me the answer for this. Fine? Hello? Hello? Are you listening? Students? Students? Anyone answer, please?
Yes.
What was the question today? Please tell me today's question. What is this today's question?
Yes, ma'am.
Today's question is what? What is the today's question? I gave you one question. I told you next class when you're coming, you should find the answer for this. What was it?
Why quantum computers build at low temperature?
Correct. Okay, fine. Okay. Again, we'll join at 12 o'clock, right? Fine. Can we join at 12 o'clock? Ma'am?
What is cryogenic?
Understood. Good. Ma'am, can we join at 12 o'clock?
Okay.
Okay, we'll join at 12 o'clock, okay? Again, you have to come at 12 o'clock. 12 to 1 will be
Okay,
next.
ma'am.
Okay.
So students take 20 minutes break and come after a break. Okay, meeting session will be started after 20 minutes.
All right.
Okay, ma'am.
Xin nhớ một câu hỏi chứ. Kalau terlalu
క్లాస్ స్టార్ట్ చేసింటారు.
Hi.
பரவாயில்ல. லல்லி லல்லி புள்ளி
Market.
Hello. Good afternoon, students. We can start now.
Yes, ma'am. Start, ma'am.
Ma'am, can we start?
Yes,
Yeah.
ma'am.
Hello, ma'am.
Yes, ma'am. You can start, ma'am. Hello. You can start, ma'am.
Hello. Ma'am, can we start? Ma'am?
Yeah, start, ma'am.
Okay, madam.
Yes,
Ma'am,
start, ma'am.
ma'am, allow me to share. Allow me to share.
Okay, okay, ma'am.
So check it. Just log in that. Sorry, ma'am. Please, everyone log in.
Make course.
Join the meeting, ma'am.
That's sir.
Everyone join the meeting. Sir asked. Okay, meeting join
Hey, Chupira. I'm lying, ma'am.
Please, everyone mute.
తినే ఒకడైతుంది పాపం డిస్టర్బెన్స్ మనం వెళ్దాం బయటకి
Everyone mute.
కారిడార్లో కూర్చో.
Hello.
ఐక్యూటీ
అందరు ఎగ్జిట్ అయ్యారు హలో అని చెప్పరా నేను చెప్తే
Ma'am, it's audible.
Yes, it's audible, ma'am.
Okay. Okay. So, please, everyone mute. So last session we discussed one
Yes,
topic.
ma'am, it's audible.
Yeah. Okay. I'll continue. So last session we discussed one topic, that is why maintaining entanglement is difficult. That because of the behavior of the qubits, and we discussed all the points like decoherence, scalability, all these are there. And now we are focusing on your syllabus. That is the next topic is error correction as a theoretical necessity in quantum system. Yes or no? Can anyone tell whether we need error correction as a theoretical necessity in quantum system? Is required? Yes, sure, it is required because of the behavior of the qubits. Your quantum information, it is fragile, and you know the reason for the causes for the fragility, that is decoherence. That is the one main thing. Since when you're trying to apply this entanglement quantum states, okay, are easily disturbed by the noise. So that gives you decoherence and operational error. Because of this flexibility, definitely we have to introduce error correction strategy in the quantum system. Next is that we have error correction code are designed to protect the quantum information. Yes, once this when your qubit is interacting with the environment, it is changing the state, collapsing, your output varies, you will get error. So definitely we have to protect the quantum information. So the use of this entanglement and redundancy across the multiple qubits to detect and correct those errors. Yes, we have. It's a definitely error correction is necessary in the quantum system. Then maintaining coherence over the time. So they want some stability. Your quantum system should work. That means we want some fault tolerant system. Okay, it should work. It should have long coherence. Yes, but it is not possible. Quantum error correction is definitely essential to extend the lifetime of the entanglement state and keep the quantum computation or your communication reliable. So our goal is we want to maintain the coherence. Long coherence should be there. Your quantum system should work stable. Always, whatever input you are giving, it should process, should get output. But there will be variation in the output because of the behavior of the qubits. Okay. So, but we have to maintain that it's not possible. So we are introducing quantum error correction to reduce the error. Okay. When we reduce the error, definitely the logical error also can be made small or it can be suppressed. Okay. Now, in essence, this the error correction is not just practical, but it is a fundamental theoretical requirement to preserve the entanglement and ensure that quantum information processing can work at scale. As you increase the number of qubits, also you have to ensure that everything is going on properly. Okay. So for these reasons, to preserve the entanglement and to ensure that quantum information processing is going on properly, as you keep increasing the number of qubits and your quantum computer size is going to increase also, we have to ensure everything is going on proper. Definitely we have to introduce this error correction. It's necessary. Any doubts in this? Okay. So the next topic in your syllabus is quantum hardware platform. Okay, at the hardware level, what are you going to use? You are using qubits, but we are using different types of qubits. Based on different type of qubits, your hardware technology used for manufacturing your quantum computer will be different. So let us see. Please mute. Please mute. Students, please mute, and your video is also on. Please mute. Please mute, students. Okay. Now we have different quantum hardware platform. The first one is superconducting qubits. So what is this superconducting qubits? One second. One second.
My student, who is that Lucky? Mute your videos. Mute your videos. Hello?
ಸರಿ 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 ನಾನು ವೇಟ್ ಮಾಡ್ತೀನಿ ನಾನು ಒಂದು ಸರಿಯಾದ hello hello okay, we'll continue now. So that we have a different quantum hardware platform. Students, it is audible?
Yes, ma'am. It's audible
Yes,
only,
ma'am.
ma'am.
Okay, okay. So if you are using this superconducting qubits, no, that this type of qubit is known as transmon. This is the superconducting charge, the use behind this concept. We are using the superconducting charge. What we are using is known as
Yes, ma'am. Audible, ma'am.
okay, is known as transmon qubits. Okay, we can say in this particular superconducting concept, when you are using we are using superconducting circuit. If you go at the hardware level, when you focus on such superconducting qubits quantum computer, they are using superconducting circuits. Here the superconducting charge known as transmon. And how the qubits are realized here, the electrical current in this superconducting loops are cooled near the absolute zero. And what is the advantage of using this particular quantum hardware platform? The advantage is that these gates are much faster and scalable. That means you can scale up nicely, and fabrication it supports for a scale up fabrication and strong industrial backing. Okay, and there is some disadvantage also is there. It has short coherence. What is this short coherence? Close my computer. So short coherence, because of this superconducting qubits behavior, it has short coherence timings. Definitely, we are looking for long coherence timings. Okay. And definitely here we require the cryogenic concepts we are applying here. That is, we are using dilution refrigerators. These are the disadvantage. When I'm using this superconducting qubits quantum computer, these are the disadvantages. And now at present, we are having these quantum computers. It is being used at IBM and Google. Okay, these are working, but it is in the range of some 16-bit quantum computer, 32-bit quantum computer. It is available in the cloud. You people also can access by enrolling there. Per month, some 10 minutes they are giving. You can work on the quantum computers. Okay, this is known as superconducting qubits, and the superconducting charge used here is transmon. It is also known as transmon qubits. So the next comes your photonic qubits. Okay, photonic qubits. Here the qubit type is photons. That is nothing but the particles of the light. Your ray of the light. Yes. So here we are trying to use this concept. How we are trying to realize this polarization path. Time being encoded photons. Okay. And what is the advantage here? These quantum computers can be at room temperature operation, easy transmission over long distance. Okay, but disadvantage is that difficult to do 2-qubit gates. Okay, deterministically, and there is a photon loss will be there. And typical uses is for quantum communication, quantum cryptography. These photonic qubits are technology is better. when you are going for quantum communication, for quantum cryptography, you can go with this photonic qubits. Okay. Next comes your topological qubits. Here the qubit type used is quasi-particle with topological states. Okay. Here how that qubits are realized, they are trying to exotic states in the certain materials. They'll try to use that. And what is the advantage here? It is expected a high error resistance. Okay. And the disadvantage is that it is still largely theoretical. Experimental realization is difficult. Okay, your future, if you go with this topological, then you can release a long coherence, errorless quantum computer. So if you follow this topological, now the research is going on this topological qubits only. If this becomes successful, definitely you can have an error-free quantum computer. That is a fault-tolerant computing quantum computing system, and is also scalable. You can increase the qubits. As you keep increasing the qubits, it is a fault-tolerant quantum computing. Now coming to next platform, if you use the quantum hardware platform, spin qubits, okay? If you use this spin qubits in semiconductors, here the qubit type, what you are trying to use, electrons, are the nucleus spins in the quantum dots. You will be using that. Now, how these qubits are realized, that is nothing but the electron spin trapped in the semiconductor material. That is the technology they are using to create this quantum computers. The advantage of this is potential for integration with the classical electronics and small size. It has a potential to integrate with classical computers, our electronics one, whatever we are trying to use. Then what is the disadvantage? Challenging to control and couple the spin, and it is having short coherence again. That is it is having a short coherence. It leads to error. That is a thing. Then it is used research in scalable quantum computing and hybrid system. Now coming hybrid, you know that they want to integrate with classical one. Okay. Now, next is that if you are using the platform neutral atoms, then these neutral atoms are trapped in the optical lattices. So that this is the qubit type we are using here, neutral atoms. And how these qubits are realized? These atoms are trapped by laser beams in regular arrays. What is the advantage of this? Large arrays are possible, and you can have long coherence. If you have long coherence, it is error free, so that you can have fault tolerant computing system. But the disadvantage is the gates are very slow and complex. Complex to control. And then what is the typical usage for quantum simulation? And you can simulate many things like this. Okay, so we have these are the different quantum hardware platform conceptual comparison we have done among the different quantum hardware platform. One is superconducting qubits, photonic qubits, topological qubits, and spin qubits, and neutral atoms. But if you want to our research is going on. Next another 2 years, if you want error-free quantum computers, you should focus on this topological one. You can, yes, this is the one going on. Now coming here, just an overview. If you're choosing this qubit type superconducting and trapped ion platform are the currently leading practical quantum computing efforts. But the photonic qubits very good. If you focus on photonic qubits, if you're using this platform, it is going to do very well in quantum computation, in communication, quantum communication for cryptography and all. If if you're working with quantum cryptography, you can go with this photonic qubits. Okay, but if you are choosing this for quantum communication, it is good, but we are facing challenges in computation if I use photonic qubits. For quantum cryptography, for quantum communication, this photonic qubits is good, but we are facing challenges in computation. The spin qubits and neutral atoms offer promising paths for scalability and integration. So when you are going with quantum hardware platforms, spin qubits and neutral atoms, definitely you can scale up the quantum computer and for integration. Okay, then yes, for integration with your classical computers. Now coming to next one is topological qubits. This is the one. It is going to promise you error-free system. That is the fault-tolerant quantum system without any errors. You can achieve. Okay, this is the early in research stage. The research is going on for this purpose only. Okay. So this is the comparison between the different quantum hardware platform. Based on the qubit types, you can have different quantum hardware. But this is not the case in our classical computer. You know, behind the technology in the classical computer, it is a transistor. Gates are made up of transistor. That is a thing. But here we have different types of qubits. Based on the different types of qubits, different quantum hardware platforms are available. Students, any doubts still here? Any doubts? Hello? Students? Any doubts? Hello? So till now we have covered all these points. What and all points we have discussed? Can anyone tell what all we covered? Hello? Yes?
No doubts, ma'am.
Okay. So what all we covered? Topics. Topic name you tell now. What all we covered? Huh? So the one is why maintaining entanglement is difficult. Another one is whether error correction as a theoretical necessity in quantum system. Then next is we compared all the different quantum hardware platforms. Okay. Okay. So the next comes your next we are going to discuss on this. Mainly you have to remember here what in this particular quantum hardware platform. Presently, whatever the quantum computer it is we are working on, it is superconducting one. Okay, that is the current leading one. Practically, we are working on now. If you want to break this, if you want to focus on this quantum cryptography, quantum communication, and you know very well, they are telling that it is very insecure in quantum cryptography security side. Hacker can break the things information very quickly within an instant. We can't tell immediately they can break the information. So if you go with this photonic qubits, it's good. If you focus on this particular quantum hardware, it is good for quantum communication, but they have a disadvantage that they have challenges in computation. Okay, and then if you focus on if you want to scale up your quantum computer, if you want to increase the number of qubits, better to use spin qubits. And if you want to integrate that with our quantum computer, if you want to integrate with our classical computer, you please go with the spin qubits and neutral atoms. And but the research is presently going on topological qubits because we want fault tolerant computing system. Okay, quantum computing system that is error free. It should work as our classical computer, how it is working, like that we should get output always. It should not change based on the environment noise. Should not change. So the research is going on this particular quantum hardware platform. That is by using topological qubits, you can build the fault tolerant quantum computers. Okay, now coming here, next is that we have to focus on this topic, that is vision and reality. Okay, so we have certain visions. Okay, some ideal goals will be there, but what in reality what we achieve, we are comparing this that. Okay, so vision is your ideal goals, and but in reality what we are trying to achieve. So once again, hello. Ah. Ah. 43437. Okay. So now we focus on the vision, that is ideal goals. Our visionary promises are, we want, first one is, as we discussed, we require fault tolerant quantum computing. That is, the ultimate goal is run long complex algorithm with error correction, no crash. Okay, there should not be no crash. Okay, next is that quantum should advantage at scale. When you try to scale up, when you increase the number of qubits, and when you're building the fastest quantum computer to solve the real world problem, exponentially it should be faster than the classical system. Then next vision is scalable qubit architecture. Okay, that is a system with thousand millions of qubits to process the millions of qubits at a time. Yes, then it is super computer, right? So that is our vision. Okay, next is universal quantum network. That is nothing but entanglement system across the globe, enabling quantum internet. That is their vision. Next vision is room temperature quantum devices. Yes, nowadays, at the present, whatever the quantum computers we are having, that is it requires some highly cooling effect. We are spending so much money for that and all, but we have to focus on room temperature quantum devices. So we have to avoid this cryogenic cooling so that we can reduce the cost and accessibility. Our next vision is secure quantum communication. Yes, another threat is in quantum computers, we have this quantum threat. Okay, so that has to be reduced. We should give more secure by using this quantum kit distribution concept, and by using giving proper quantum algorithms, cryptography algorithms, we should be able to secure the quantum communication. That is unbreakable encryption using entanglement and quantum principle. Next is that next vision was quantum simulation of complex material, to simulate the molecules, materials, and chemistry to complex classically. So these are all our visions. Okay, just you think of when we are able to scale up the any number of bits, million qubits. If I'm able to construct a quantum system, a fault tolerant quantum system, and I have a full-fledged facility to scale up. How many bits you want, you can increase, and no error only. Just think the speed of your quantum system, what you can achieve at the universe level. Okay, so that is our vision. But what is happening in the reality? Okay, that is not the reality now, because you know your quantum system are fragile and it is error prone. The reality is we are working on that. Research is going on. As I said, they are using this topological qubits to overcome all this. Okay, fine. But the reality, what is working now is we have small scale quantum processor. Okay, what is the thing? These systems with 50 and 100 plus qubits, it can process. Okay, already it is existing. These quantum computers, people are working on that. It is supported by this IBM company and Google, IonQ. Okay, all this. Now coming to next is the reality, we have quantum supremacy demonstration. That is Google's scheme over 2019 outperformed the classical in a narrow task. So this is the one reality is going on now. Okay, then we have high fidelity qubit control. Yes, one concept in the building the quantum computer conceptual overview is we should be able to control the qubits, right? Okay, but the reality is high fidelity in qubit control. Okay, so single and 2 qubit gate fidelities, they are telling it is greater than 99% in some platform. Okay, and next is whatever the quantum error detection. Okay, the basic forms of error detection and small core demonstration. Okay, we are able to detect the errors, and we are trying to use some concept like no cloning theorem, and we have some threshold theorem and all we are applying, and we are trying to manage the errors when we try to detect the errors. Next comes at the present scenario, we are using this quantum communication experiment. We try to do this on the communication side when we are sending the data from one quantum information from one side to another side. How secure it is, okay, by using the concept quantum key distribution, teleportation across the some kilometer distance. This test is going on, this experiment is going on communication side, so that to provide the secure quantum communication. And we have cloud quantum computing for public access to quantum devices via cloud platform. As I said, your IBM is providing this, you can check this. Okay, you can use the quantum computer provided by this IBM cloud and AWS cloud. Okay, this is the present scenario. Presently, this is the facility available on the quantum computers. Any doubts, students? Any doubts? Students, any doubts? Hello? Okay, students, any questions? Huh?
Students,
Any questions?
Already said that.
Okay, what I'm trying to do, I'll upload all this in the website. I'll create one Google site. I'll upload all these PPTs and also the notes. You can go through. If you have any questions, you can ask me. Okay, today we will close the session.
We used to keep the trend for
Okay, today we will close the session. Any doubts, students? Any doubts? Okay. Okay, we'll close the session.
Yes.
Ma'am, Malti
Ma'am.
ma'am.
Yeah, ma'am.
I'll close the session today. For today, I'm closing the session.
Okay. Thank you for doing the session, ma'am.
Okay, ma'am. Thank you very much.
Okay, ma'am.